Hi, welcome to this lecture on building a computer. Here's an outline for the lecture. We're first going to talk about representing information on a computer. So we want to represent different kinds of information such as numbers, letters, strings, and so on. And also things like pictures, audio, and movies, and such on a computer. So that's what we're going to discuss first. And then we will talk about Boolean algebra and Boolean functions. And then we will discuss how you construct electrical circuits with which you can perform logical operations. And then we'll talk about doing arithmetic with logic. And then we will discuss how you construct a memory module. And then finally, we will discuss how you build an entire computer using what is called the von Neumann architecture. All right, so let's get started. Now, at the very basic level, a computer is just manipulating electric signals according to some specific rules. Now, if we want to make those rules produce something useful, something meaningful, we need to associate those electrical signals with numbers and symbols because we are more comfortable working with numbers and symbols. So let us start with integers and see how those can be represented on a computer. To represent integers, computers typically use combinations of numbers that are powers of 2. And this representation is called the base 2 representation or the binary representation. So let's take an example. So let's say we have the 4 consecutive powers of 2, which are 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. Now with these 4 powers of 2, we can make all of the integers from 0 through 15 using just 0 or 1 combinations of these guys. All right? So for example, the number 13 can be written as 0, 1 combinations of these 4 powers as shown here. Okay, so it's 1 times 2 to the 3 plus 1 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0. So we say that 13 in decimal is simply 1101 in binary, right? In other words, 1101 in binary is simply this expression which evaluates to 13, right, in decimal. Let's take another example. Let's say we want to represent the number 9 in binary. All right, so 9 in decimal can be written as some combination of the powers of 2. So I'm going to write the powers of 2 here. So the question is, how much of 2 to the 3 or 8 do we need? Well, I'll take 1 of that. So that gives me 8, so I'm left with 1. Now, do I need any of 4? Well, I don't, because if I include 4, then I'm going to overshoot 9, right? So I don't need any of 4. What about 2? Well, the same thing. If I take 2, I'm going to overshoot 9, because all that I need is 1 to fill the gap, all right? So I take 0 of that, and then finally, I'll take 1 of 2 to the 0, which is simply 1, right? So what I'm saying here is that 9 in decimal is simply 1001 in binary, right? Okay, now in a similar fashion, 603 in the decimal system really means it is 6 times 10 to the power 2 plus 0 times 10 to the power 1 plus 3 times 10 to the power 0. And why are we considering powers of 10 here? Well, because we are talking about the decimal representation of a number, right? And in that case, these combinations, these coefficients that we consider take on values between 0 and 9. All right, so 6, 0, and 3, they're all values between 0 and 9. Now, in another base, such as the octal base, the number 207 really means 2 times 8 to the power 2 plus 0 times 8 to the power 1 plus 7 times 8 to the power 0, which if you carry out the arithmetic, you get the number 135. Right? So what we are saying is 207 in base 8 is simply 135 in base 10. And here, since we are talking about base 8, the powers that we consider are powers of 8. All right, and the coefficients are values between 0 and 7 because the base that we're considering is 8 here. So in the general case, if we choose some base b greater than or equal to 2, then it turns out that we can represent every positive integer between 0 and b to the d minus 1 using d digits, right? Where the coefficients take on the values between 0 and b minus 1. So to take an example, let's say we are talking about the binary base. So b is 2. And let's say we fix d to be 4, meaning we are representing number just using 4 bits or 4 digits. Since the base is 2, the coefficients can only be 0 or 1, right? And what is the range of values that we can represent? Well, it is between 0 and b to the d minus 1. So it is between 0 and 2 to the 4 minus 1, which is 15. And that is exactly what we said here, in that using these 4 powers of 2, we can represent all the numbers from 0 through 15 using 0 or 1 combinations of those powers. All right. Now, in a modern day computer, we are typically representing numbers using 64 bits, which means that you can represent integers as large as 2 to the 64 minus 1 on such a computer, okay? Because d here is 64. So according to this rule, the largest number that you can represent is b, which is 2 here, to the power 64 minus 1. All right, so and that's a pretty big number. So you can work with very large numbers on a modern day system. Okay, so that's how we represent an integer, or at least a positive integer, on a computer. Now let's talk about arithmetic. Right? Now arithmetic in any base is analogous to arithmetic in base 10. So let's first look at how you add two numbers in base 10. So here is how you do it. So let's say you're adding the numbers 17 and 25. So how do you carry out the addition? Well, you first add 7 and 5, which gives you 12. So you write the 2 down and then you carry 1. And then you add these guys and you get 4, which is what you write here. So 17 plus 25 is 42. Now you use a similar approach when you're adding numbers in binary. So what I'm showing you here are two binary numbers, 111, which is 1 times 2 to the power 2 plus 1 times 2 to the power 1 plus 1 times 2 to the power 0, and that is 7. And this guy here is 1 times 2 to the power 2 plus 1 times 2 to the power 1 plus 0, and that is 6. Right? So if we add 7 and 6 in decimal, we get the number 13. Now the question is, how do we carry out this addition in binary? Well, it's the same idea. You first add 1 and 0, which gives you 1. That's what you write here. Then you add 1 and 1, which gives you 2. But what is 2 in binary? It's 1, 0. So you write the 0 here and carry the 1. And now you add these guys. 1 plus 1 plus 1 is a 3, which in binary is 1, 1. Just think about it. So you write one of the ones here, and the other one you carry. And then there's nothing here, so you simply bring this guy down, and this is the result that you have. Now the question is this the binary representation for 13? Well, it is. So let's check that out. So what this is saying is, it is 1 times 2 to the power 3 plus, 1 times 2 to the power 4, it is 3. So it's 1 times 2 to the power 3 plus 1 times 2 to the power 2 plus 0 times 2 to the power 1 plus 1 times 2 to the power 0. So this is 8 plus 4, which is 12, plus 0 plus 1, which is 13. So this is indeed the binary representation for the number 13, right? So that's how you carry out addition in binary. It's very similar to how you do it in decimal. Now, how do you represent a negative integer? Well, for that, we use what's called the 2's complement approach, right? So if I have a positive integer, the way I figure out the binary representation of its negative value is using a two-step process. I first take the binary representation of the given number and flip all the bits. So that's the first step. And then I simply add 1 to that result, and whatever I end up getting, that's the binary representation for the negative of the given number, right? So let's look at a concrete example. Let's say we are on an 8-bit computer where all the numbers are represented using 8 bits. Okay, so how is 3 represented on such a computer? Well, it is that. It is 6 zeros followed by 2 ones. Okay, so that's 3 in binary. Now the question is, how do we figure out the binary representation for -3? Well, it's the two-step process called the 2's complement approach. You first flip all the bits to get 1, 1, 1, 1, 1, 1, 0, 0, and then you simply add 1 to that result, all right, using the approach that we talked about here. So this is going to give you 1, 0, 1, 1, 1, 1, 1, 1, all right? And that is -3, right? Now, when you take, so in the decimal system, when you take a number and add to it the negative of the number, you get 0. So the question is, do you get the same when you add in binary a number to its negative? Okay, so let's check that out. So this is the binary representation of -3, and 3 is this. So just add these two guys together. So 1 plus 1 is 0, carry of 1. 1 plus 1 is 0, carry of 1, 0, carry of 1. 1 plus 1 is 0, carry 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 1. 1 plus 1 is 0, and then you carry 1. Okay, now this is 0. Okay, so you have 8 zeros, and then the 9th bit here is 1, but that's completely ignored because we are on an 8-bit computer. Okay, so this is all that matters, and that is 0. Okay, so this representation is quite consistent. A number plus its negative gives us 0, as we would expect. So now we know how to represent an integer, positive and negative, in binary. Now, let's talk about representing real numbers. What if we want to represent pi on a computer? Well, for that, we establish a convention, okay? So let's say we use the base 10, and let's say we only have 8 digits to represent our numbers. So we can come up with a convention that says the first 6 digits out of the 8 digits is for the fractional part of the number, and the remaining 2 digits is for the exponent. Okay, so that's a convention that we fix. So for example, using that convention, this 8-digit number, an integer, 31415,901, represents this number here. Why? Because we said that the first 6 digits represents the fractional part. So these guys simply represent the fractional part. Okay, 0.314159, and then this part here represents the exponent, and since we are in base 10, it is 10 to the power 1. Okay, so what is this then? Well, it is simply 3.14159, and that is an approximate value of pi. Okay, so this is how, using a convention that we come up with, we represent a real number on a computer just using an integer. All right, so computers use a similar idea to represent fractional numbers. All right, so what next? So the next thing is to talk about how you represent letters and strings. Because one of the things that you commonly do with a computer is you work on documents, you write documents, right? So what is a document? A document is basically a string of letters or symbols. So we need to figure out how you represent strings of letters, okay? So in order to represent a letter or a symbol numerically, what we need is a convention, right? We basically need a mapping that maps a letter to a number, so that then we can represent any symbol or letter just as an integer, okay? And such a mapping was established by the American National Standards Institute, or ANSI for short, and this mapping was called ASCII, and ASCII stands for American Standard Code for Information Interchange. Okay, so what this convention is that it's basically a table that maps a symbol to a number. Okay, so ASCII defines encodings for uppercase, lowercase letters, numbers, and a set of special characters, right? And each of these symbols has a number associated with it, okay? Now, ASCII is an 8-bit code, which means that you can only represent 256 different symbols using ASCII. So ASCII does not provide for characters used in many languages, such as Chinese, for example, all right? So why is it that with ASCII you can only represent 256 different symbols? Well, it's going back to the idea that we talked about before. It's an 8-bit code. So what is the largest number that you can represent? Well, it is 2 to the 8 minus 1. So you can represent all the numbers from 0 through 2 to the 8 minus 1, and there are 256 of those. Okay, so using ASCII you can only represent 256 different symbols. So what if you want to represent characters from a language like Chinese? Well, for that you need to go beyond ASCII, and that's what the International Standards Organization, or ISO for short, did when they came out with the 16-bit Unicode system. Right? So there is provision for representing every known language, and there is room for more. So you can have additional characters. Right? So here the range of values that can be represented using the Unicode system is, again, going back to the idea that we discussed before. It is 0 through 2 to the 16 minus 1. And that's a pretty big range of values, right? Now, if you're just working with English, then Unicode is somewhat wasteful. So you don't want to represent each symbol using 16 bits. So for that, ISO has defined what are called Unicode transformation formats, or UTF for short, and the most popular UTF format is the UTF-8 format, right? Okay, so now we know how to represent a symbol or a letter as an integer, using one of these encodings, either ASCII or Unicode or UTF-8. So how do we go from there to representing strings? Or a document, for example, because a document is nothing but a string of letters. It's very easy. So a string is basically represented as a sequence of numbers, along with a length field that specifies how long the string is, or how many characters that string has. So for example, in ASCII, this sequence of numbers would represent the string chocolate, right? And the length field in this case would be set to 9, because the string has 9 characters in it. Okay, so the way the string chocolate is going to be represented internally is as a sequence of 10 numbers, starting with 9 and then all these numbers following that. Okay. And what are these numbers? Well, these numbers are basically the ASCII encoding for each of these characters. So in ASCII, C maps to 99, H maps to 104, and so on and so on and so on. Okay, so it turns out that we can represent any information as a sequence of numbers. So for example, a picture can be represented as a sequence of pixels, each represented as three numbers giving the intensity of red, green, and blue at that pixel. All right, because a picture is something that looks like that. So each of these cells is a pixel, and the picture itself has some height, some width. Now for each pixel, we need three numbers. So we need an R value, a G value, and a B value. And each of these values is a number between 0 and 255. All right. So for each pixel, we need three 8-bit numbers, and we need a total of 3 times W times H 8-bit numbers to represent a picture that has a width of W and a height of H. Okay, so the bottom line is that a picture can be represented simply as a sequence of integers. Okay. What about an audio signal? Well, an audio signal is simply a signal, an analog signal that looks something like that. Okay, so how do we represent this on a computer? Well, what we do is we discretize the signal. So we chop it up along the time axis into these discrete values, and it's the sequence of these values that I'm highlighting using these dots that we use to represent the sound signal. Okay, so what we're saying is that this sound signal can be represented as a sequence of these numbers which represent the sound pressure levels. All right, so sound is nothing but a sequence of numbers as far as the computer is concerned. Okay, what about a movie? Well, a movie is nothing but a sequence of pictures, right? At a certain frame rate, 30 frames per second or whatever. Okay, now, and then there is also an accompanying audio that goes along with the sequence of pictures. We know how to represent each of these pictures using this idea here that we talked about, and then we also know how to represent the audio signal as a sequence of numbers. So a movie then is nothing but a sequence of numbers, one sequence per frame, along with another sequence of numbers representing the audio part. Okay, so the bottom line of this discussion is that every piece of information can be represented using numbers on a computer. All right. Okay, so now let's talk about Boolean algebra and Boolean functions. So Boolean variables are variables that take on one of two values, true or false, 1 or 0, on or off, and so on. And with Booleans 1 and 0, we can use operations or functions called and, or, and not to build more interesting Boolean functions. Okay, and we'll see some examples of that. Now, a truth table for a Boolean function is simply a listing of all possible combinations of values of the input variable along with the output that is produced by the function. Okay, so let's look at the truth tables for the basic Boolean functions and, or, and not. Let's start with AND. Now, AND is a binary operation. What that means is it has two inputs, each of which is a Boolean variable. So let's call these inputs X and Y. All right. Since there are two inputs, each of which is a Boolean, how many possible values do we have for the inputs? Well, we have 4 of them, 0, 0, 0, 1, 1, 0, and 1, 1. Okay, and that's what you see listed here in the truth table. Okay, and what about the output? Well, the way the AND function works is that the output is a 1 precisely when both inputs are 1, and it is 0 otherwise. All right, so both inputs have to be 1 for the output is 1, for the output to be 1, otherwise the output is simply 0. So that's the truth table for the AND function. And then we have the logical, we have the OR function. That's also a binary function in that it has two inputs, and since it has two inputs, the truth table has four rows, four combinations for the values of the inputs. And the way the output works for the OR operation is that the output is a 1 when either of the inputs is 1, right? And the output is a 0 exactly when both inputs are 0. Okay, so that's why you see a 0 here when both inputs are 0, and you see a 1 otherwise. Okay, and then finally we have the NOT function. The NOT function is a function of one variable, one Boolean variable. And since there is just one Boolean variable, the number of rows you have is 2, just two possibilities. X can be 0 or 1. And the output is extremely simple. It's the opposite of the input. So if X is 0, output is 1. If X is 1, the output is 0. Okay, so those are the truth tables for the basic Boolean functions and OR and NOT. And these truth tables are going to be extremely important for us going forward. All right, so make sure you understand how these functions work. Now it turns out that any function of Boolean variables, no matter how complex, can be expressed in terms of the basic Boolean functions and OR and NOT. And let me illustrate that with an example. Let's consider the proposition which says if you score over 93% in this course, then you will receive an A. All right. Now, the truth table for this proposition is given by what is called the implication function, which is denoted using this symbol, right? And it is the truth table is shown here. So there are two inputs, X and Y, and here is the output column. Now, what we call X is this part of the proposition, and what we call Y is this part of the proposition. All right, so let's try and reason the values in here. So the output is a 0 precisely when X is 1 and Y is 0. Okay, why is that? Because if X is 1, it means that you've scored over 93% in the course, and Y equals 0 means that you did not receive an A. But that is means that the statement is incorrect, because if you according to the proposition, if you receive a score of over 93%, you ought to get an A. So in this case, the output is a 0, and for all other cases, the output is a 1. Okay, so if you scored less than 93% and you did not receive an A, then the statement is true. Right? If you scored less than 93% and if you got an A, the statement is still true. So this is actually somewhat tricky to grasp. Right? You did not score over 93% and yet you received an A. That doesn't mean the statement is false. You might have done something amazing in the course that your instructor decided to give you an A, right? But so that doesn't falsify the statement itself. So we have a 1 here. And then we have this scenario where you did receive over 93% and you got an A, and that sticks to the proposition. Okay, so that's the truth table. Now, the question is, how do we build a Boolean function for such a table? Well, here is a Boolean function that represents this truth table. Meaning, if you plug in the values for X and Y, you will retrieve this Boolean table, this truth table, right? And the Boolean function is simply not X or X and Y. And an alternative notation for this is shown here. So not of X is also so not of X is also written as X bar, and then X or Y is also written as X plus Y, and X and Y is also written as X immediately followed by Y. So this is just alternative notation, all right? And it's somewhat compact. Okay, so This is a Boolean function that represents this truth table. So now the question is, how do we arrive at such a function given the truth table? And that's what we're going to talk about next. So the question is there an algorithm that would take a truth table, an arbitrary truth table, and build a formula, build a function, a Boolean function from it? And it turns out that there is such an algorithm. It's called the min-term expansion algorithm, and it's due to a very famous person by the name Claude Shannon, who did some amazing work in the field of information theory. Right? So this algorithm provides a systematic approach for building Boolean functions from truth tables. So let's see how that works. So the first step in the process is to write down the truth table for the Boolean function that you're considering. And then we simply delete all the rows from the truth table where the value of the function is 0. Okay? So if you see a row where the output is 0, simply delete that row. Now for each remaining row, what you do is you create what is called a min-term. And you do that by following these two steps. All right? And the way you build a min-term is by looking at each input variable, and if that variable has a value 1 in that row, you write the name of the variable as is. And if that variable has a value of 0, you write the variable with a bar on top of it, meaning the not of that variable. Okay? And now you combine all these variables together using the AND operation. Okay, that's how you get the min-term for one row. You repeat this step for all the rows. Okay, and then once you have the min-term for each and every row, you combine them all using the OR operation. Okay, so that's basically the recipe for turning a truth table into a Boolean function. And let's see how that is done, or how the algorithm is applied for the implication function. So shown here is the truth table for the implication function, and notice that we have erased the row that has 0 for the output. That's the very first step in the algorithm. We only keep the rows that have 1 for output. Okay, and what we do is we build a min-term for each row. So how did we get this min-term for this row? Well, x, the input variable x had a value 0, so we write it with a bar on top of it. Right? Y had a value 0, write y with a bar on top of it. And then you combine them using the AND operation. Here for this row, x had a value 0, so you write x bar. Y had a value 1, so you write y. You combine them using the AND operation. And here both x and y had the values 1, so you write xy. Right? So once we have the min-term for every row, we combine them using the OR operation. So that's how we get a Boolean function, or a formula that represents a truth table. Right? Now, it turns out that this formula is absolutely equivalent to this one that I showed you before. And you can check that. You can just plug in values for x and y, and you'll see that you correctly retrieve the truth table for the implication function from either of these formulae. Right? So now the question is, given a formula such as this, is there an algorithm to simplify it to something like that? Well, the answer to that is no. So finding the simplest form of a Boolean function is provably as hard as some of the hardest problems in mathematics and computer science. Right? In other words, there is no algorithm that can take an arbitrary Boolean function and simplify it. All right? Okay, so now let's talk about electrical circuits and how you use these circuits to perform logical operations. Let's start with an electromechanical switch. So an electromechanical switch can be represented using a schematic as shown here. So you have some power that is applied here, some input applied here, and you receive the output here, right? Now, there is always some power applied here, and you receive output only when the input is high, meaning there is some input here. Because when you apply some input, this switch is going to close, and this input is going to appear here at the output. So when input is high, output is high, and when input is low, or there is no input, there is no output. Okay. Now we can slightly modify this setting to derive the truth table for the NOT gate or the NOT function. And here is how it's done. So we have some power applied and we receive the output here, and then there is some input that is applied here. Now when there is no input, we receive some output via this path, right? And when there is some input, the switch kind of releases from here and we receive no output. Okay. So what we are saying here is when the input is high, the output is low, and when the input is low, the output is high. And that's exactly the truth table for the NOT operation, right? So we have managed to sort of like build something that computes the NOT function. What about the and the or functions? Well, we can combine two electromechanical switches in this fashion to get the truth table for an and function. Why is that? Well, there is some input here, and then there is some power that is applied here. We receive some output here, and these are the inputs. Okay. Now we get some output precisely when both inputs are high. So when both inputs are 1 or high, these switches are going to close, and we receive some output here, right? When either of them is open, we receive no output, and that is precisely the truth table for for the AND function. What about the OR function? Well, we apply some power here, and these are the inputs, and here is the output. And as you can see, as long as one of the switches is closed, meaning one of the inputs is high, you're going to receive what is applied here at the output terminal. And you don't receive anything here precisely when there is no input applied to X and Y. Okay? And that is exactly the truth table for the Boolean OR function. Okay? So by arranging electromechanical switches in these fashion, we can basically compute the Boolean and the Boolean OR operation. Now, modern day computers do not use electromechanical switches. Instead, they use what are called transistors. Okay. Now, transistors are much smaller. They're very much faster and more reliable and more efficient than electromechanical switches, right? And that's what we use in modern day systems. But they work in a similar fashion. So the principle of operation of transistors is exactly the same as electromechanical switches. Okay. Now that we know how these switches work internally, what we can do is we can abstract away the details, right? And we can simply look at these switches as black boxes. And this is the symbol that we will use for representing an AND gate. And this is the symbol that we will use for an OR gate, and this is what we will use for an OR gate. And we don't care henceforth on what goes on inside of these things. All that we are interested in is what the inputs are and what the output is going to be. And that is completely given to us by the truth table, right? Now, since we have a Boolean function that represents the implication function, which is this, that we got by applying the min-term expansion principle to the truth table for the implication function, what we can do is we can build a circuit that computes the implication function, and that circuit is what is shown here. So you have a logical OR gate which basically has 3 pins for each of these guys, and they are combined using the logical OR operation, right? That and that. So that's what this gate does. This gate here computes X bar, Y bar. Why is that? Well, look at how this input comes in for this AND gate? Well, it is X passed through a NOT gate, right? So what you get here is simply X bar. What about this one here? Well, it is Y after it passes through a NOT gate, so this input is Y bar. And what this gate does, since it's a logical AND gate, it simply does an AND operation on these two guys to get X bar, Y bar. And similarly, you can convince yourself that this gate here computes X bar Y, and this one here computes XY, right? So this circuit is now something that you have in hardware that computes the implication function. The output here can be related to the input here using the truth table for the implication function, right? So if you just plug in the values for X and Y and figure out what the output is, you'll see that that output is exactly what is given by the truth table for the implication function, right? Now let's talk about doing arithmetic with logic. So what's shown here is the truth table describing the addition of two 2-bit numbers to get a 3-bit result. All right. Since X is 2-bit and Y is 2-bit, the number of rows that we have here are 16 because there are 4 possible values for X and 4 possible values for Y. Right. So we have 16 rows here, and then the output is a 3-bit result, because when you add 2-bit two 2-bit numbers, the largest number that you get for the result is 6, which is 3 plus 3, and 6 cannot be represented using 2 bits. You need at least 3 bits. Okay, so here's the truth table. Now the question is, how do we build some hardware that actually computes this? Okay. Now we can sort of naively do that using the min-term expansion principle. Okay, so what we do is we focus on each column. We focus on each column here, and then we apply the min-term expansion principle. Right. So for each column, we're going to get some circuit, and that's and then once you have that, you can build some hardware out of that computes this truth table. But that is quite tedious, because, for example, if your inputs are not 2-bit numbers but they're 16-bit numbers, so in that case you're going to have a huge number of rows in the truth table, because for X you have 2 to the 16 possibilities, for Y you have 2 to the 16 possibilities, so the total number of rows is that times that, which is 2 to the 32. Right? And then the result itself is going to be a 17-bit number. All right, and for each of those columns you need to apply the min-term expansion principle, which involves looking at these many rows, which is a huge number. So the circuit that you're going to end up with is going to be extremely infeasible. It's going to have billions of gates. So that's not the approach that we want to seek. So what we do instead is we build a relatively simple circuit called the full adder, right? That just does one column of addition. So here is a schematic for a full adder. It has 3 input pins called X, Y, and carry in, and it has 2 output pins called Z and carry out. And here is the truth table for the full adder circuit. All right. So let's see how we get this truth table. So let's take this particular row. So X is 0, Y is 0. So X and Y are 2 1-bit numbers. So the possible values here are 0, 1, 0, 1. And let's say the carry in is also 0, and carry in is also a 1-bit number. Okay. So how do we figure out C out and Z? Well, you simply add these guys. So when you add these guys, you get 0. So the output is 0. There is nothing to carry out. All right, so this is similar to what we did when we talked about adding two numbers in binary. Okay, let's take another example. Let's take this one. X is 0, Y is 1, and there is a carry in. Okay, so what are these guys? Well, add these guys together. 0 plus 1 is 2. But what is 2 in binary? It is 1, 0. So you write 0 here and you carry 1 out. Okay, so that's how you get these two values. Let's take another example. Let's take this one. So you have 1, 1, and 1. You add them together, you get 3. But how do you write 3 in binary? You write it as 1, 1. So one of the ones goes here and the other one is carried out. So that's how you get these two values. Okay, so this is the truth table for this particular black box. Okay, which we call the full adder. Now, what you can do is you can apply the min-term expansion principle to this truth table, and you can get a formula for z, which is what is shown here, and you can get a formula for C out, which is what is shown here. And once you have these Boolean functions or Boolean formulas, you can easily make like circuits out of those. Okay, similar to using an idea similar to what we did for the implication function. Now, how did we get some of these terms? So how did we get that? Well, it's very simple. You focus on this column, and we get rid of all these rows because those have a 0 for output. And for the remaining rows, you build min-term. So how do you build the min-term for this guy? Well, it is x bar because x has a value 0, y bar because y has a value 0, and cin, right? Because cin has a value of 1, combined using the AND operation. So that's how you build these min-terms. And then once you have them, you combine them using the OR operations. Okay, and once you have done that for z, you do the same thing for C out. Okay? You eliminate all the 0 rows, so all those guys are gone. And for the other rows, you compute the min-term. So to get that, what you do is you take x bar, because x has a value 0, y has a value 1, and cn. Right? So that's the min-term for this row, and that's what you see here. Okay, so we know how to turn this truth table into hardware then, all right? And that hardware, what is it capable of doing? It is capable of adding two 1-bit numbers to give you a 2-bit result. And now what we can do is we can take n full adders and we can chain them together to get something that can add two n-bit numbers. Okay, and the resulting circuit is what we call a ripple carry adder. And shown here is a 2-bit ripple carry adder. Okay, so this one can add two 1-bit numbers. This one can add two 1-bit numbers. You chain them together in this fashion. So C out of this guy is the C in of this guy. C in of this is 0, and so on. Then what we have is basically a circuit or a black box that can add two 2-bit numbers, okay, to give you a 3-bit result. All right, and you can chain, for example, 16 of these guys to get a circuit that can add two 16-bit numbers to get a 17-bit result. Okay, and these circuits are fairly straightforward to build. They're quite feasible. Okay, so now let's talk about memory. How do you build a memory module in hardware? Well, for that we need the notion of a NOR gate, and the NOR gate is basically the opposite of OR gate, and the truth table is shown here. So the output in this case is a 1 precisely when both inputs are 0, and it is 0 otherwise. So this output is exactly the opposite of the OR gate. All right. Now a latch is a device that is able to save or lock a bit and retrieve it later. So it's basically a 1-bit memory module. And once we have a latch in place, we can combine any number of those to get what we call the random access memory. So you can take 1 billion latches, put them together, and you have a gigabyte of memory, right? Now the question is, how do you build a latch? How do you build a 1-bit memory module? Well, you combine these NOR gates using this configuration, all right? And that can remember a bit of information. So let's see how that works. These pins are called R for reset and S for set. And Q is where we receive the output, and Q bar is the opposite of Q. Okay, so let's start with R equals 0, S equals 0, and Q equals 0. Okay, now if Q is 0, this pin here is also going to be a 0. And if these two guys are 0, the NOR gate says that the output ought to be a 1. Okay, so this guy now is a 1. Okay, and things are consistent, so Q and Q bar are the opposites of each other. Now let's say we turn this bit to 1. Okay, so what happens in that case? Well, this is a 0, this is a 1. So if you go to the table, we see that the output should be a 0. So this guy now is a 0. If this is a 0, you have a 0 here. All right. Now, if both of these guys are 0, then the NOR gate output is a 1 from the truth table. So what we have managed to do is remember this bit here. Okay. And it's going to remember this bit as long as this circuit is powered up. And once you pull the plug on the circuit, it's going to forget this information. And that's exactly how RAM works on a computer. It remembers things as long as the computer is powered up, right? And loses all that information when you unplug the computer. That's why we call a RAM a volatile, okay? All right. Now we are ready to talk about how you build a computer. Okay. Now in a modern computer, the CPU or the central processing unit is where all the action takes place, right? What does the CPU contain? Well, the CPU has devices such as the ripple carry adders, multipliers, and so on for doing arithmetic. And in addition, it also has a small number of very precious memory that are called registers. Okay, but you only have a small number of those. Now, in addition, the computer has what we call the main memory or RAM, which allows storing large amounts of data. And the main memory is separate from the CPU, and it is connected to it by wires on the computer's circuit board. Okay. Now, a program that you write is typically a long list of instructions, and that's something that is stored in the main memory. You cannot possibly store a program inside of the CPU because you have a tiny amount of memory in the form of registers inside of the CPU. So the program resides in main memory, and it is copied into the CPU one instruction at a time and then executed. All right. And the CPU has two special registers, which are called the program counter and the instruction register. Now, the program counter keeps track of the location in memory where it's going to find the next instruction to execute, and that instruction is fetched into the instruction register and executed. Okay? That's how things work. Now, this way of organizing computation is due to a very famous mathematician and physicist, John von Neumann, and hence this architecture is called the von Neumann architecture. Let's get somewhat concrete and talk about a particular example. So it turns out that instructions, just like data, can be encoded as numbers. Okay. And let's say we have an 8-bit computer that allows only 4 arithmetic operations: addition, subtraction, multiplication, and division. So we want to talk about how you represent instructions on these on such a computer as numbers. Okay. So the first thing that we need to do is map those instructions or operations to numbers, and that's very easy. There are just 4 operations here, and hence we just need 2 bits of information to represent all 4 operations. So here's the mapping. Add is represented by the number 0, subtract by the number 1, multiply by 2, and divide by the number 3. Okay. So we have managed to represent all the operations as numbers. Now let's assume that this computer has 4 registers which are numbered 0 through 3. All right. And in binary they are 0, 0, 0, 1, 1, 0, and 1, 1. And let's also assume that the computer has 256 8-bit memory cells. Okay, that's the main memory that this computer has. Now, here is how an instruction is going to be encoded. It's going to be encoded using 8 bits because we are on an 8-bit computer. The first 2 bits are going to represent the operation, add, subtract, multiply, or divide. And the next 2 bits are going to represent the destination register, which is the register that is going to store the result of the operation. And then the remaining 4 bits are going to encode the registers containing the 2 inputs or the 2 operands. Okay. So let's say that the instruction is add 302, which means we want to add the values in the register 0 and 2 and store the result in the register 3. So that's the instruction. So the question is, how is this instruction represented as a number? Well, it's extremely straightforward. Add from this table is simply 0, 0. Okay, so that's the 2 zeros that you see here. That stands for add. The next 2 bits represents the destination register, which is 3. And 3 is 1, 1 in binary. And the next 2 bits represents one of the 2 operands, 0. Okay, 0 in binary is 0, 0. And the last 2 bits represents this register, register number 2, which is 1, 0 in binary. Okay, so this instruction is represented as this binary number. Okay, now this is what we call machine language, and this is what we call assembly language. Okay, now you can see that it is incredibly difficult to write a program in machine language because you have to write it as strings of zeros and ones. Very, very tedious. You don't want to be doing that. It's much better to write programs at this level using an assembly language because it is at a higher level than machine language. And in fact, in the next lecture, we are going to learn about an assembly language called HMMM, where we will be writing code along these lines using high-level instructions, and then we will use a program to translate that code into machine code, right? And then we will execute that machine code, but we won't be writing code at this level. We will be writing it at this level. Okay, now how does a computer typically execute a program? Well, it works as follows. It sends the address in the program counter to the memory and it asks it to read that location. Okay, because remember that the program counter, PC for short, stores the location in memory where it can find the next instruction that needs to be executed. And that instruction is fetched into the instruction register. And then the instruction register is decoded because we need to figure out what the operation is that the instruction encodes. And we also need to figure out information about the output register and the input registers and so on. Okay, so once we have decoded that instruction, the computer then executes that instruction. Okay, which involves reading the operands from registers, performing arithmetic, and sending results back to the destination register. right? And once that instruction is executed, the PC, the program counter, is incremented so that it contains the address of the next instruction in memory that needs to be executed, right? And then this whole process is repeated all over again. That instruction is fetched into the instruction register, it is decoded, executed, and then the PC is updated again, and the next instruction is fetched, and so on and so on. So let's look at a concrete example. So let's say, so here what we have is the CPU and the main memory, and the program counter is has this value, which is the location in memory where the next instruction can be found, and that instruction is fetched into the instruction register. Okay, and that's the instruction that is first decoded. Well, what is this instruction? Well, that is add, and that is the destination register, which is 2, and that is one of the two operand registers, which is 0, and that's the other register, 1. So we are saying add the values in the registers 0 and 1 and store the result in 2. And that's what is going on here. We take this value, which is 5 and decimal, and this value, which is 2 and decimal, add them together, and we get 7. And this is indeed the binary representation of 7. Okay, so we have taken the values in registers 0 and 1, added them together, and stored the result in register 2. So we have managed to execute this instruction, and then the program counter gets updated to the next instruction that is fetched in, executed, and so on and so on and so on. So that's how a program is typically run by a computer. Okay, so with that, we are done with this lecture. Thank you for your time.